Let's just finish up the discussion of strings, because this is actually the difference between Python 2 and Python 3 that took me a while to get straight. In Python 2 and C, 1 byte is 1 character. So if you have a series of characters like hello, it's just a series of bytes. And I was so used to that, I always thought that was true. And that is no longer true in Python 3, or for that matter, Rust, or Go, or any other modern language, for a very good reason, because you can't express non-English languages in that simple a system. So in Python 2, you can just put bytes in, like \x41 is 1 byte, and this is byte 42, and this is FF, and you get a series of bytes. But if you do it in Python 3, it doesn't work. You get an answer, which I found very confusing at first. So let's look at this. All right. So this is how you put literal hexadecimal bytes in Python. You use \x and then 2 digits of hex. So this is the byte 41, which is capital A, and here's 42, which is capital B. So then I put in FF, which is not a valid ASCII character. And when I look at that character, I get this weird foreign character, Y with umlaut. So that's a little strange, why it even tries to print some character when I put in an invalid code. But what's even weirder is to see the bytes. And here's how you get back to the bytes. You encode the string back to bytes, and then you can print the bytes, and you will see the first byte is 41, which is what I expected, and the second byte is 42, but the FF turned into 3 bytes, C3BF, which is very strange. So if you give it a weird value that is not encodable as ASCII, it will turn it into a 2-byte code. And what's going on here is it's Unicode. And Unicode, Microsoft, as we're going to see later, uses an old-fashioned 16-bit kind of Unicode, which was a bad idea, but it's what Microsoft standardized on. The more modern version of Unicode is like the IP version 4 address space. You take half of the possible bytes, and those are for the old ASCII, and those are single-byte characters. Then you take more of the space, and those are 2-byte characters, and some are 3 bytes, and some are 4-byte characters. So an individual character can be up to 4 bytes long, and it varies character by character. And a string is a list of characters of varying size. This is the right way to store a string, so you can have Arabic and every other language in the world in there. There's enough bytes for everything, but it means you can no longer think of a character as being a one-to-one match with a byte. Not at all. Characters are just these objects, Unicode objects. So a \x is a literal byte, and a \u is a Unicode character. So if you try a few of these, here is the \x41, that gives you an A. That's the literal A. If you try to put that in Unicode, though, it won't take it. It won't take it with 2 zeros or 4 zeros. The only Unicode version it will take in Python is 4 bytes. But it will only store 1 byte because it removes the leading zeros. So this is kind of rude, but that's the only format it will take. And so if you encode it, it goes back to an A, but the B before the quote means this is actually a byte array containing a single byte, which encodes for the ASCII character A. So anyway, that's the joy of Unicode. And these things are called Unicode code points. So now we can get a little bit more clarity about what happened with that FF. If I put in the FF here, that turns into the Y umlaut. And this, of course, it won't take it because it wants me to put zeros in front of it. 1, 2, 3, 4, 5, 6. All right, and now that is the Unicode point that codes to Y umlaut, which is C3BF. And so you can find every character in Unicode. Since there's 2 million possible code points, they've got emoticons and all the foreign characters and everything, but they're just these strange Unicode objects which are from 1 to 4 bytes long. And anyway, That's the main difference between Python 2 and Python 3. Python 2 treats an array of bytes as equal to a string, and in Python 3 they are completely separate objects.